Today we're going to continue our study of quadratic functions. In order to do that, I'd like to launch the lesson with a couple warm-up problems that are going to get your brains thinking. So pause the video right now and spend some time working through number 1 and number 2 using all of the key features and characteristics of quadratic functions that we've been studying. Once you have had time to finish numbers 1 and 2, then we will press play again to hear my explanation. Now that you guys have done numbers 1 and 2 on your own and worked and checked your answers as a group, I want to talk through how I would reason through numbers 1 and 2. So for number 1, it says without graphing, determine the function. So we're not graphing by hand, but when I'm looking at this, I know that minus 6 on the inside, I'm just going to create a sketch at least. I'm not going to graph all of the points or make a table or anything like that. But I know that minus 6 on the inside translates it to the right 6. 1, 2, 3, 4, 5, 6. The plus 2 on the end translates it up 2. So I know I'm going to have a vertex of a positive 6, positive 2. I don't know how wide or narrow it's going to be, but I see that negative out front, which in my head I'm thinking, okay, that's going to reflect it, so it's going to be opening down. So it'll look something like that. So then when I go to the rest of this, the axis of symmetry, well, my axis of symmetry goes right through my vertex. And so that's going to have the equation of x equals whatever the x-coordinate of my vertex is. X equals 6. So my axis of symmetry is x equals 6. And now my domain and range. Domain, well, this, if I look at the x values going left and right, because it goes forever to the left and forever to the right, there's no starting point or ending point left and right, then I'm going to say that the domain goes from negative infinity to infinity, or we could say all real numbers, either way. If I'm looking at the range are my y values, and y goes up and down. And when I'm looking at this, I have a maximum here, and that maximum value is 2, which means everything else is below 2. So if I'm doing interval notation, I know my maximum goes on the right. So if the maximum is 2, I can write that on the right. It actually hits 2, so I'm going to have a bracket. We're going to include that. And then if I go down forever, I go down to negative infinity, I'm going to have a parenthesis because I actually never reach negative infinity. That's interval notation. If I want to use an inequality, I can look at this and say, okay, well, this is where y is 2. Everything else is below 2. So it will be y is less than or equal to 2. And then finally ask for the transformations from the parent function. And when I see the word transformations, I'm thinking translate, reflect, and vertical stretch or shrink. So when I look at this, I know that I was translated to the right, translate right 6, and up 2 units, but it's also opening down. So there was also a reflection. So if it opens down, there's a reflection in the x-axis. And so those are my transformations from the parent function. Moving on to number 2. Number 2 gives me an equation, and it says that equation has an axis of symmetry at x equals 1 and an x-intercept of 4, 0. It says, how could you prove that this is quadratic function? Because when I look at this, normally we see quadratic as x squared, but I don't see an x squared. So there's a couple different ways to do this. Initially, I'm thinking we did a lot of this last unit in the polynomial unit, where if I did x minus 4 times x plus 2, I could multiply that out either using the area model of the box, x minus 4 and x plus 2, in which case I do x times x is x squared, x times negative 4 is negative 4x, 2 times x is 2x, 2 times negative 4 is negative 8, and I combine like terms, and I see that I would get x squared minus 2x minus 8. Or I use the double distributive property. I say, well, that's really equal to x times x plus 2 minus 4 times x plus 2. And then if I distribute here, I get x squared plus 2x. I distribute here, I get negative 4x minus 8. And if I combine like terms, I get that same x squared minus 2x minus 8. So I can clearly see the degree is 2 and it's quadratic. If I asked you this on a quiz or test, not only would you show some kind of work like that, you'd also have to write a sentence explanation explaining that. So I would explain that the degree is 2, the highest exponent is 2. But you didn't have to do this. We talked yesterday about how helpful it is to have a graphing calculator. Let's go ahead and graph this in the graphing calculator. So I have parentheses x minus 4, x plus 2. And if I go to the graph, I can see the graph is a parabola. So my argument could say on the graphing calculator, I see the graph as a parabola. It's got to be quadratic. It just doesn't look like the form that we're used to seeing. Or look at your table. Your table, what we see is if I scroll up here, it tells me it has an axis of symmetry at x equals 1. So let's go to where x is 1. look at that vertex right there. You got the symmetry on either side. So you could also explain using the table in the graphing calculator. So lots of different ways to verify that this is a quadratic function. So then it says find the other x-intercept. So if I look in here, this is the x-intercept 4, 0. We have our axis of symmetry at x equals 1. So if that is an x-intercept, I know that a parabola is symmetrical, and it's symmetrical about the vertex. So when I look at this, if this x-intercept is 3 to the right, then I could go 3 to the left of that axis of symmetry and plot my other x-intercept there. Okay. So I would have the point -2, 0. It says explain your strategy, so I'd want you to write a sentence explanation, but it could look, your explanation could look different depending on how you chose to do it. I think if the one x-intercept is 3 to the right, the other one would have to be 3 to the left of the axis of symmetry. Another way that I know that students have thought through it in the past is you look at a table. You have x and y. If the vertex is going to be on the axis of symmetry, we have 1, that's our symmetry, and then one x-intercept is 4, 0. You can look at that. Well, that's plus 3. So to go the other direction, I'd have to minus 3. So that would get me at -2. And I should have symmetry there. So you could either look at it using the table or the graph. So then it says use the equation to prove the point you found falls on the parabola. So we're testing the point -2, 0. If you think back to first semester, we did a lot of this, verifying that that point was a solution or on that function. We were typically doing on the line. But if I look at this, if I have y equals x minus 4 times x plus 2, I can substitute in x is -2 and y is 0, and if I get a true statement, that point is on that parabola. So I have y is 0, -2 minus 4, -2 plus 2, and I just simplify. The left-hand side's already simplified. If I use order of operations and I simplify the right-hand side, -2 minus 4 is a -6, -2 plus 2 is a 0, and I get 0 equals -6 times 0 is 0. I get a true statement, so that point is on the line, or sorry, on the parabola. Or going back up here, if you have your graphing calculator, let's look. Your other x-intercept, we had one at 4, 0. The other one is at -2, 0. I could find that using my graphing calculator and verify that as well. So lots of different ways you could verify that point falls on the parabola. If you have a graphing calculator, you can type in the equation and look at your table. If you don't, you can substitute into the equation. Scooching down, it says determine the y-intercept of the function. So when we do this, we got to think back to what we know about y-intercepts. Y-intercepts are where x equals 0. So here it's going to be somewhere along that y-axis where x is 0. If I look at this, I know that the parabola is opening up because we have a positive number out front, so +1. So the parabola will look like this. So I know the y-intercept has to be below the y-axis if I'm going to get that U shape opening up, but I don't know exactly where it's going to be. So this again is where your graphing calculator could be helpful. If I go here, I'm looking for where x is 0 in the table. Boom, I got my y-intercept is -8. But if I don't have a graphing calculator, I can still answer this question. So I just need to know that that's when x is 0. So I go back to my equation, y equals, and I substitute 0 in for x. And then I can simplify. 0 minus 4 is a -4. Again, I'm using order of operations, simplifying inside the parentheses first. 0 plus 2 is 2. And now there's that imaginary multiplication. I simplify and I get -8. So my y-intercept will have the coordinates of 0, -8. And I can plot that point now right here. So then part E says, how can you use the y-intercept to find another point on the parabola? Well, if we just look at the graph again, that y-intercept is 1 unit to the left. So to get another point, I could go 1 unit to the right to keep that symmetry, and that would be the point 2, -8. Again, if it asks you how can you use it, I'd look for a sentence explanation if I was asking this on a quiz or test. So you could talk about how you are 1 unit to the left of the axis of symmetry and you need to go 1 unit to the right. Again, the other way to look at that is the table. If you know that the axis of symmetry, we're going to be symmetrical about 1, and I know that we have 0, -8, then if I'm 1 to the left, I'd have to go 1 to the right, 2, and it should be symmetrical, -8 as well. So there's another point. All right, so then part F says, is it possible for the vertex of the parabola to be 2, -8? Well, if 2, -8, it would be right here. And what we see is that that's not possible because the vertex in this case is going to be the minimum. It's a parabola opening up, so we'll have a lowest value. And you can't have that lowest value be straight across. You'd end up getting a horizontal line if we had 2, -8. So it's got to be lower. Now, I don't know if it's at 2, -9 or 2, -10. I'm not really sure. But it's got to be below that -8. And even if you look in the table, you know you have to change. You can't have 3 numbers in a row right here. That vertex has to be different. So this one would be no, and you can explain that in a variety of ways. For G, it says determine the vertex of the parabola to complete the parabola. Show your work below. So if we look at this, I know the vertex has to be on this line of symmetry, right? It can't be up here. We said if it's a parabola, it's going to be opening up, so that vertex has to be somewhere down here. I know that the x-coordinate would have to be 1. I just don't know the y-coordinate. But just like before here with our x's, or when we found the y-intercept and we had x was 0, we knew x was 0, we didn't know y. You can substitute that x value in to find your y-coordinate that corresponds to that x-coordinate. So this means x equals 1. I want to know what y equals, and so I have this equation, y equals, I can substitute 1 into the equation. And when I simplify, I get -3. 1 minus 4 is -3. 1 plus 2 is 3. -3 times 3 is a -9. So the y-coordinate is -9. So my vertex will have the points 1, -9. And then when I look back at here at the graph, that makes sense because now I have this parabola. And I can see that that vertex would make sense. There's another way to find the vertex here besides substituting in, and those that have graphing calculators, that is what you want to be trying today. So if you go to y equals, and I have this in my calculator, you can look at the table, and we can clearly see that the vertex in the table is -9 because, like you guys have told me in the previous few days, we have symmetry around that vertex. So you could just use your graphing calculator and find that. Or if you go to the graph, this is what I want to show you today. If you hit the graph, we can see where it looks like it's about, but there's actually a way to do this on a graphing calculator that will find you the exact minimum in this case, or maximum if it was opening up, the exact vertex. In order to do that, you're going to go to your calculator, and you see where it says calc? It's in blue. You're going to calculate that vertex. So I go to second to get that blue, and I press calc. When you look at the list, think to yourself, which one of these do you think I'm actually trying to find? We know that 0 is just another word for x-intercept. Well, I don't want the x-intercept. I look down here, I see minimum and maximum. Yes, those are the things I'm talking about when I'm thinking vertex. So the graph, because we have a parabola opening up, our graph has a minimum. So I'm going to choose number 3. And now it says left bound, which means, is this cursor, the one that you see moving here as I move to the left and to the right, is that to the left of the vertex? And we see that it is. So I'm going to press enter, and it can be anywhere to the left. And now it's asking you for the right bound. So I use my arrow button, and I move over until I'm to the right of the vertex. Okay, I'm clearly to the right of the vertex now, so I'm going to press enter again. Well, now it says guess, and all it wants you to do is it wants you to move it closer to the vertex. Okay, so we're pretty close to the vertex there. Press enter. And what we see is we have 1.00000, y equals -9. Now that's really close to 1. And that's just an error on the calculator's part. We're going to round that to 1. So when x equals 1, y equals -9, that would be my vertex, which is verified by the calculations we did down here, as well as when we were looking at the table in the graphing calculator. And what I'd like to do today is focus on how can we use that function on our graphing calculator to continue to find minimums and maximums. All right, so that was our launch. What I want us to do now is flip to the back of this page and start working through the notes. In order to do this, let's read through it, and I want you to spend a little bit of time doing numbers 1 through 3. So I want you to take a break on 4, because 4 is going to require us to fill in the blanks. So take a break on 4, but just do numbers 1 through 3. So pause the video, spend time on your own doing numbers 1 through 3, and then check your answers in your group, and then you can press play for the video again, and we will go over numbers 1 through 3. So press pause and work on 1 through 3 right now. All right, now that you guys have done numbers 1 through 3, I want to talk through my rationale for these. It says Aaron shoots a water bottle rocket from the ground. A graph of the rocket's height over time is shown below. So we see the graph. Okay, I'm looking at this. I see a U-shaped graph. I'm thinking it's a parabola. We start on the ground. We end on the ground. We have a maximum. Just kind of processing what's going on here. Okay, so now I look here. What equation below could model the function, and how do you know? I'm just going to go step by step and kind of talk through my rationale. So I look at y equals 4x. Well, I'm looking at that, and this is linear. That would be a line with a slope of 4 and a y-intercept of 0. That's definitely not going to match the graph because the graph's a parabola. I look down here, I don't see an x squared, but I do see an x times an x, and if I were to distribute that, that would be negative x squared plus 5x. So I'm thinking, okay, that's quadratic, which gives me that. I don't know where the vertex is because it's not in what we call vertex form. We don't see it like this where you see the transformations. So I'm going to table that right now. It's at least quadratic. I know I see the u shape. So then I go down here, and this function is in what we call vertex form, meaning you can find the vertex from the equation because we see the transformations. We see a plus 6 at the end, which tells me that it goes up 6, and a minus 2.5, which means it goes right 2.5. And if I look at this graph does look like it goes to the right 2.5. So that would be good. Going up 6, we go up. Well, we actually go up a little higher than 6, so I don't know about that. I'm not too sure about that. But let's keep that in mind. So the other thing I'm looking at, though, is that this parabola is opening down. When I see a parabola opening down, I know that the number up front has to be negative. We got to reflect that in the x-axis. And I don't see a negative here. So I actually know for sure that C is not correct. When I look up here, I have that negative out front. It's opening down. It is quadratic. This is the only one that's logical. I don't see the transformations, though, because, again, this isn't a different form. This is standard form because we have the x squared and the x. Or it was originally in factored form. We used those vocab terms in our previous unit. So this is factored form. I converted it to standard form. But if I look at my graphing calculator, if I go to y equals, clear out the equation I used to have. If I have negative x times x plus, sorry, that's minus 5, and I go to my graph, okay, that graph looks like it's about right. It keeps going on forever, which it doesn't here, but you have that at the origin, it goes up, comes back down, looking at about 1, 2, 3, 4, 5. Yeah, that looks about right. I can go to the table, and I see I have 0, 0, which is where I start here. I go up. At 2 and 3, I have at 6 and 6, which that makes sense, and then 2.5 is in between. That's where my vertex is going to be, so I don't actually see the vertex in the table, but I do see that we're symmetrical about it. And then when I go back down, I see it has an x-intercept at 5, 0, which it looks like. So yeah. If I have a graphing calculator, I can definitely confirm that. Even if I don't, I can still look at it and analyze, and I'm good to go. All right, so then number 2 says the axis of symmetry of a parabola is a vertical line that divides the parabola into 2 congruent halves. I actually kind of already drew it in right here. It says sketch a dashed line where we believe the axis of symmetry would fall on the graph, which I did, and then write an equation for that line. So because it's a vertical line, I know it's x equals, and we're between 2 and 3, and we're exactly 2 and exactly 3, so exactly in the middle would be 2.5, right? So then the challenge becomes is number 3, approximate the rocket's maximum height, then use the equation in order to find the exact value. Well, when you look at this, I know that it's above 6. It's definitely not to 7. I wouldn't even say it's in the middle. So I would say like it's about 6.1, 6.2, 6.3, something like that. So that would be my approximate. So I'm going to say somewhere 6.1, 6.2, or 6.3. That's where I'm guessing. That many meters above the ground. But now I want to use the calculator or the equation in order to find the exact value. And you can do this 2 different ways. If you do it the way we did on the front, if we know that the vertex is on here, we know that the x-coordinate is 2.5, I can find the y-coordinates. We have x equals 2.5, y equals, don't know, but got to find out. I know it's somewhere above 6 and below 7. So I can go back to my equation, and you can actually use either one of these equations. You can say y equals negative, I substitute 2.5 in for x. Negative 2.5 is right there. 2.5 minus 2.5 is a negative 2.5. And when I multiply these together, I end up getting 6.25. So pretty close to what I was approximating. I could also do it over here. Y equals negative 2.5 squared plus 5 times 2.5. I have to follow order of operations. Remember, this is like negative 1 times that. So exponents first. 2.5 squared would be 6.25 plus 5 times 2.5. Let me do that in my calculator. It's not coming to me in my head real quick. That's plus 12.5. So negative 1 times 6.25 is a negative 6.25. And when I add 12.5, I get a positive 6.25. So we can see either way, either equation, because they are equivalent, you should get the same vertex, which looks about what we were saying before. So this is 2.5 comma 6.25. Now I want to show you on the graphing calculator how you could also figure this out. So if you go to your graphing calculator and go to y equals, I already have that equation typed in. If we look at the table, we know that the vertex is happening somewhere between where x is 2 and 3, because we see that right here. So I could go to my table, and if you see table set, right above window, if I press second and window to table set, it says table starts at -1. That doesn't really matter where it starts because I can scroll up and down. But the delta table says, what do you want the x's to go by? Right now we're going by 1, so x is going to go 1, 2, 3, 4, 5. If I change that to 0.5, now I can have the x's go by 0.5. So let's look back at the table. Now I see -1, -0.5, and so on. So I want to go to where x was 2.5, and now I can see that symmetry on either side, and I see that it's 6.25 in the middle. That's one option. I'm going to go back to the table set and change that back to 1, because that's what I'm used to seeing. But that was one option. I could also go to the graph, and I see the graph again right here. And again, because this graph has a maximum, a highest point, when I go to calculate, second calc, I now go down to number 4. And it's going to ask me for the same questions. Left bound? Yep, I'm to the left of the vertex. Right bound? Scooch over to the right. I'm to the right. Now guess. Well, I can make close. Press enter. Yep. That's 2.49999. That's really close to 2.5, so we're going to round it to 2.5, and we get 6.25. So there's lots of ways you could find the exact value of the vertex. All right, and then number 4. So now that we said if all you knew that was at the vertex was 2.5, comma 6.25, and the point 4.5, comma 2.25 is on the graph, what would be the coordinates of another point you could find on the graph? My recommendation is go plot this point on the graph and see if you could figure out another one. Pause the video right now, try number 4 on your own, and then check your answer with the answer in the video. All right, now that you've done that, let's scooch up. If I go to 4.5, comma 2.25, that's right here. We have 4.5, comma 2.25. Again, there's always multiple ways to think through this. My thought process is that I got to be symmetrical around the axis of symmetry. So from the axis of symmetry, I'm going to the right. Well, if that's at 2.5, to go to 4.5, I'm going to the right 1, 2. So I go to the right 2 units. It means I could also go to the left 2 units, 1, 2, and plot another point. So if I was at 2.5, to the left 2 would be at 0.5. I stay along that same y value. I'm not moving up and down. I'm just symmetrical about the x-axis. So this would stay 2.25. So the point 0.5, comma 2.25 is another option. Another way you could think about this is if I scooch down and I draw the table. I have my table, if this is x and y. I have the vertexes 2.5 and 6.25. And then if I have the point 4.5, comma 2.25, I know I need to be symmetrical about the vertex. So if that's my vertex, over here I should have 2.25, and it should be the same distance away. So if I added 2 to go this direction, I could subtract 2 here and get 0.5. Either way, I can reason through that the point 0.5, comma 2.25 would be on the graph. The rest of these are additional practice problems that if you want to go back and do them, you can, or if you got to them while you're waiting for others to catch up, you could do that. I'm going to show you my answers now. If you want to jot them down or take a picture or refer to this video later, you can, but we're not going to spend more time in class going over these. These are just extra problems that would be useful for you as we're preparing for quizzes and tests. All right, and for the last part, if we have time, this last part, if there's not enough time, that is okay. But if you do have additional time, I wanted to practice using the graphing calculator. And so here, we're going to look at quadratic functions. We saw in the previous problem that there's different ways to write quadratic equations. So we have 3 different forms. So when you see an equation written in the form where you can easily identify the vertex, it's going to look like y equals a times the quantity x minus h squared plus k. In other words, you see the quantity squared, and you can see the translations. You're either adding or subtracting inside, adding or subtracting at the end. Factored form is what we did in polynomial unit, where you see y equals, you might still have a number out front, but it'll be x plus or minus something, x plus or minus something. So up here, the equation would look like y equals maybe 3 times x minus 4 squared plus 10. Over here, you might see y equals, maybe there's a number, maybe there's not. Let's say there's not a number. This might just be x minus 5 times x plus 2. And then over here, standard form, we talked about converting from factored form to standard form. If you multiply that all out, you'll get an equation that looks like ax squared plus bx plus c. And so if I were to multiply this out, I would end up having y equals x squared. I'd have a positive 2x and a negative 5x. I get negative 3x, and then a minus 10. So like this would be an example of standard form. So what I want you guys to do is remove the context. We're not talking about story problems. I want you to identify the quadratic function, whether it's in vertex form, factor form, or standard form. So for A, for each one of these, you'll just write what form you think it is. And then your job is to find the vertex. Now sometimes we can identify the vertex right from the equation. Sometimes we can't. So you can use your graphing calculator. If you can't figure out what the vertex is just by looking at the equation and using transformations, then you can use your graphing calculator and enter the equation in and use the methods that I showed you earlier in this video to find the vertex. Once you've done that, you can sketch the picture and you can answer the following questions. The domain and range and interval of increasing and decreasing are all things that we've done the last few days in Algebra 1, and so I want you to use that knowledge again to do the rest of these problems. I will show you my answer key, so I want you to pause the video, do this on your own, but then you can check your answer with my answers here. So this is what I got for my answers. I will scan these in and have them on the course website as well. I've also done where if you find the y-intercept from the graphing calculator, you can reflect that and what additional point that would be. So if you want extra practice with if you take the y-intercept and reflect it, what you could get, you guys can do that and look at your answers here. So you can spend the rest of the hour doing that. Use your graphing calculator, try and figure these information out on your own, and then use this video and the answer key to check your answers. If there's not enough time to do this in the class, do not worry. This was additional practice if we have time.